Hello everyone. So in this video, I'm going to continue expanding on the ideas that we are learning in chapter 4. As I said, this is a chapter that is quite important in class because it sets the fundamentals idea for reactions in organic chemistry. So before I talk about acidity and basicity, we learn to use curved arrows to show the flow of electrons now in reactions. And then we discuss acidity in terms of pKa first, and secondly, in terms of molecular structure. Here we are going to learn something a little bit more advanced. So, question here is, what happens if you have a reaction with a molecule, say for example acetic acid, in which you have two sites that can be acting as a base? So you could be a little confused now. Acetic acid is an acid. Usually behave as an acid. Remember the pKa of acetic acid is 4.8. However, in chemistry, and this is why I'm bringing this example, it all depends on who are you facing with, your molecule. In this case, I'm mixing acetic acid and sulfuric acid. And when you look at the pKa values, you can see how acetic acid, you know that the pKa is 4.8. Positive pKa is a weak acid. And sulfuric acid has a negative value of pKa, is a very strong acid, almost fully dissociated. So if you make these two, obviously sulfuric acid will be acting as an acid in the reaction, and acetic acid should be acting as a base. Structurally, what does a molecule should have to act as a Lewis base? Basically, it must have heteroatoms with electrons. Remember, Lewis base is a species that can donate electrons to form a new covalent bond. We have two oxygen atoms here with electron pairs. So at first, if acetic acid acts as a base, we have two basic centers, two basic sites, potential basic sites in this molecule. So the question that we raise here would be, which of these two sites will be reacting with sulfuric acid? Obviously, the one reacting will be the more basic. So the question translates into which of these two sites is more basic. Same thing happened over here. This is carboxylic acid, acetic acid. Here we have an amide functional group. So the amide functional group reacting with hydrochloric acid. So here is obviously hydrochloric acid will be the Lewis acid. It will be accepting electrons in this hydrogen because this HCl bond is highly polarized. And when we look at the molecule of acetamide here, which will be acting as a base, once again we have two potential basic sites. We have a nitrogen with electron pairs, and we have an oxygen with electron pair. So the question will be here once again, which of these two sites will be acting as a base? Which of these two is more basic? So you will find in the future molecules that are acting as bases and might have potentially different basic sites, and you will need to determine which one is the more basic. Or the opposite. You can have a molecule with two different acidic sites. And I will give you an example of that too. So when you have more than one site that can be reactive in the molecule, you need to determine which one is the more reactive. So in these two examples, let's focus on the first one, acetic acid and sulfuric acid. Sulfuric acid is the acid. We have two potential basic sites. Which of these two sites is more basic? The answer follows the same reasoning that we learned before. Remember when we determine acidity, when we have to classify molecules in terms of acidity, the more acidic is the one with the more stable conjugate base. Here is the opposite reasoning. We need to determine within the same molecule which of these two sites is the more basic, the one leading to the more stable conjugate acid. Okay, so remember once again, if you compare molecules in terms of acidity, the more acidic is the one leading to the more stable conjugate base. If you compare two molecules in terms of basicity, the more basic will be the one with the more stable conjugate acid. It's the same reasoning. In this particular example, it's just one molecule with two basic sites. Which one is the more basic? The one leading to the more stable conjugate acid. So let's analyze here. Here is the molecule of acetic acid. Here is sulfuric acid. And these are the two potential conjugate acids. So one will be the result of protonation in the carbon and the oxygen. So this oxygen acting as a base, one lone pair forming a new covalent bond. Now the oxygen will be positively charged. That's one possibility. The second option will be protonation in the hydroxylic oxygen, leading to this positively charged oxygen over here. Since the question here is which oxygen is going to be protonated, the answer is which of these two conjugate acid is more stable. Okay? So, in this case, we are looking at stability of conjugate acids, not bases. It's oxygen, so now it's basically following the opposite reasoning that we analyzed for basicity, for conjugate bases. In this case, because we're talking about conjugate acids, we're talking of species that are positively charged. So let's look first where is a positive charge located. Here is over an oxygen, and here is over an oxygen. Even though oxygens are highly negative, you do not want positive charge on highly electronegative atoms, remember. In both species, the positive charge is over the same atom. So we cannot think about electronegativity. If you were to think about electronegativity, obviously the less electronegative will be the more stable conjugate acid, right? Opposite reasoning as with bases. But in this case, it does not apply. Same atom. We cannot think about electronegativity, we cannot think about size, we cannot think about anything. So what's the difference in between these two? Well, there is a factor of the fifth factor that we analyzed before that is applies resonance. So let's draw the resonance structure for each one of them and see what can we conclude out of that. So if we protonate in the hydroxylic oxygen, we get this cation here, okay? And now, remember, one resonance structure will be by flowing these pi electrons of this oxygen leading to this. So in this resonance structure, we have now negatively charged oxygen, but look at what we have here. Two unlike charges positive adjacent to one another. So one unlike charges over here and two positive charges next to one another. Obviously, this is something that will make this structure a very minor contributor. Remember, you cannot even think about moving these electrons over here because that will create an oxygen 2+, much less likely. So protonation in the hydroxylic oxygen leads to a cation that is barely stabilized by resonance because of the positive charge over here. And let's look at what happens with protonation in the carboxylic oxygen. Protonation of the carbonylic oxygen leads to positively charged carbon, and now this structure compared to this one, remember how we talk about resonance structure that don't exist, but we have priorities to determine which one contributes more, for example. So this is a resonance structure, and then we can flow these electrons over here to get to this resonance structure. Okay, so now Protonation to the carbonyl oxygen leads to a cation that can be stabilized by resonance, and in fact the positive charge now is shared between the oxygen, the carbon, and the second oxygen. Obviously the structures 1 and A3 contributes the most because they have a full octet. So protonation in the hydroxylic oxygen leads to a structure that is barely stabilized by resonance. Protonation in the carbonylic leads to a structure, to a conjugate acid that is highly stabilized by resonance, and the positive charge is shared in between the atoms. Because of this, we can conclude that the conjugate acid resulting from protonation in the carbonylic oxygen is more stable because of resonance, and therefore the carbonylic oxygen is more basic. Okay? Let's look at another example. And here we are looking at the reaction in between this functional group and hydrochloric acid. So this is an amide, and this is hydrochloric acid. So hydrochloric acid will be acting as an acid, and obviously then this molecule will be acting as the Lewis base. The Lewis base must contribute with electrons to form a new covalent bond. And once again, we have two potential heteroatoms here with lone pairs, oxygen and nitrogen. Therefore, in this case, we once again have to determine in this molecule which site is more basic, the oxygen, carbonylic oxygen, or the nitrogen. To determine which one of these two is more basic, we need first to draw the structures of the conjugate acids. So the conjugate acid resulting from the protonation into the amide functional group will basically have a proton bonded here. And protonation here will lead to obviously a positively charged nitrogen. Apologize for the. Okay, so if the nitrogen is acting as a Lewis base, these two electrons are used to be, and I'm gonna use now an arrow here. These two electrons will be used to bond to form a bonding and I'm gonna color code this so you guys can see it. So I'm gonna color code this as red. So protonation in the nitrogen means the lone pair of the nitrogen being used to bond, form a new covalent bond with this hydrogen, which is acidic, and then the electrons going to the chlorine to form the chloride atom. So that leads to this covalent bond, which is new, and then obviously a positively charged nitrogen. It has 4 bonds. Protonation in the carbonylic oxygen in this case, I color coded blue. Okay, same thing here, forming one covalent bond, and then the electrons going to the chlorine atom. Okay, so that will lead to the protonation in the carbonylic oxygen will lead to a species that is positively charged on the oxygen. So let's draw that. So one pair of electrons is gone because that is used for the new covalent bond. New covalent bond here with the oxygen and the hydrogen, and then the oxygen obviously will be positively charged. Okay, so this is the conjugate acid resulting from protonation, the one on the left to the nitrogen and the one on the right, the conjugate acid resulting from protonation in the carbonylic oxygen. So if we want to decide once again which of these two sites is more basic, we need to look at the stability of the conjugate acids. The conjugate acid resulting from protonation in the amide is clearly not stabilized by resonance because the pi electrons are now used for this new bond. There is no lone pairs of electrons here anymore. So the only thing you can do here to stabilize is basically this as before, and this is going to lead to two positive charges next to one another. The conjugate base resulting from protonation in the carbonatic oxygen clearly can also be stabilized. This one can be stabilized by resonance. And in that case, you will have another significantly contributing structure. I'm not drawing the one with a carbon positively charged as in the slide, but obviously you can also do that. So this will lead to a double bond here, and then now the nitrogen is going to be positively charged, and then clearly the oxygen is not going to be positively charged anymore because it will have now two bonds. Okay, so this will be the two significant contributing structures, and as you can see, protonation in the carbonylic oxygen leads to a conjugate acid that can be stabilized by resonance, and the positive charge is shared in between these two atoms. There are also some potential sharing with the carbon if you just draw the structure from the carbonate. Therefore, if you react an acetamide with hydrochloric acid, if an amide functional group acts as a Lewis base, the protonation will take place at the oxygen only. Why is that? Because it's the most basic site of the both of them. And the reason for that is because it leads to the most stable conjugate acid. Okay? I'll show you now a last example, but a reason, an opposite reason. So let's say I'm going to give you a molecule like this. Okay, and then let's say I react this molecule with a very strong base. I'm going to say a generic base. Okay, B minus. I'm going to say A minus. The computer is thinking that is boron. Okay, so let's say we are going now to react the molecule with a very strong base. If this is the case, this molecule will be acting as a Lewis, sorry, so as a Lewis acid. So this is the base, so this one will be acting as a Lewis acid. And the moment we look at a molecule acting as a Lewis acid in this case, we need to look at the molecular structure in order to determine what? The most acidic proton. Okay. So let's look at if you're looking at a more complex molecule like this, first thing you need to think of is how many non-equivalent protons do we have here. These points you guys are familiar with equivalency. And I can see that I have protons here next to 3 protons here that are equivalent, but these 3 are bonded to an sp3 carbon, nothing really close to them. So these 3 are very low acidity, really very low acidity. But let's look at the rest set of protons. You have 3 here, 2 here, and 2 here. These are sp3 carbons at first, right? They are sp3 carbons. And what happens with them? They have next the carbon functional group. There's three of them. So what I'm gonna do is I'm gonna draw, if I don't know which of these protons are gonna be taken, okay, I'm gonna draw here, let's say hydrogen. I'm gonna draw another hydrogen here. And I'm going to draw another hydrogen here. I'm gonna color code them. I'm gonna repeat the idea again because this is really important. You will see this a lot in organic too as well. That's why it's so important that you guys understand this. So I have three. So I have, once again, a molecule here reacting with a strong base. So I need to think. This molecule is going to be acting as a Lewis acid. Where? What is the reaction site of this molecule? If it's going to be acting as an acid, I need to look for the most acidic site, the most acidic proton. And what I'm looking at is the protons that are different. So this is a set of protons that is equivalent. This is another set. There are two here. There are two here. These three, I'm going to look into them because there are three bonded to an sp3 carbon that has named sp2 close to them whatsoever. So I'm going to discard anything you see bonded to an sp3 with nothing electronegative close to it or sp2 hybridized. You have to discard that. Very low acidity. And then if I don't know which of these three is the most reactive site, and I have to make a decision of which of these three protons is more acidic, how do I answer this question? So basically, I need to think which of these three protons is the most acidic. That's my question. So the answer is going to be which is of these three protons leads to the most stable conjugate base. Same reasoning. I'm going to draw then the three potential conjugate bases over here. It's very important to jump steps, okay? So, once again, molecule acting as an acid, where? What is the most acidic proton of this molecule? The one leading to the most stable conjugate base. So let's draw the conjugate bases. So removing the green proton leads to a carbon ion at that position. So the green proton will lead to a carbon ion here. Okay. Removing the blue proton will lead to a carbon ion, obviously in the blue carbon bonded to the blue hydrogen. Which I'm going to color code. And removing the red proton will lead to a third carbon ion. So these are the three, and once again, guys, doing this one thing at a time to make the conclusion of what is the most reactive site of this molecule as an acid, what is the most acidic proton. To determine the most acidic proton, you need to look at the conjugate bases, the most stable conjugate base. That's why we have to draw all of them. Okay. And now let's analyze the three conjugate bases and see what can we find to determine stability in them. The negative charge here is over the carbon, the negative charge here is over the carbon, and the negative charge here is over the carbon. Three negative charges on the same atom. cannot think about anything like electronegativity. I cannot think about size. I cannot think about hybridization state. So what is the factor here? Resonance. The moment we have a negative charge next to a double bond, this can be delocalized. So the the green proton, the green carbon ion can be stabilized by resonance with this carbonyl functional group over here. So the negative charge is going to be sharing between the carbon and this oxygen. The red carbon ion can also be stabilized by the same, right? So it has a carbonyl functional group next to it, so the charge can be delocalized over this carbonyl functional group. So the charge is sharing between this carbon and this oxygen. And the negative charge, the conjugate base with the negative charge in this carbon, this can be stabilized toward this carbonyl, but can also be stabilized toward the second carbonyl, because it has two ways of delocalizing, toward the left and the right side of the molecule. Remember, delocalization brings stability. So from the three potential conjugate bases, clearly the deprotonation of the center carbon leads to the most stable conjugate base because of resonance. Because of the delocalization. So the negative charge is delocalized here between 1, 2, and 3 atoms, these three. If you do the resonance structure, you will see that the negative charge here is sharing between only 2 atoms, here in between only 2 atoms. Therefore, the more delocalized the charge, the more stable is the conjugate base. Therefore, the most acidic proton is blue. Okay? So this is a reasoning that you guys need to understand and apply in organic chemistry. When you face molecules with potentially different reactive sites, you need to think which one is the most reactive. In order to come up with the answer, you have to go one question at a time. First question is it acting as a Lewis base or as a Lewis acid? In this case, it's acting as a Lewis acid, reacting with a very strong base. If it's acting as a Lewis acid, what are the potential acidic hydrogens? I'm going to focus on hydrogens that are bonded to highly electronegative atoms, right? In this case, it's bonded to an sp2 that is more electronegative than an sp3. This one is bonded to 2sp2, and this one is bonded to another sp2. I am not considering this one because this one is not bonded to anything electronegative, sp3. So that's why I first discarded this and I focus on these three sets. Acidity comes from polarization in covalent bonds. Okay, so you look for hydrogens bonded to highly electronegative atoms. Once you focus on these three, to answer the question which one is more acidic, draw the conjugate bases. Conjugate base from green, conjugate base from blue, conjugate base from red. And now we need to determine which one is the most stable. In this case, the factor is resonance. The one that is most stabilized by resonance is this one. Therefore, blue is the most acidic proton. Therefore, this one here will be the, if you treat this compound with a base, the resulting product will be this. None of these two will be formed because the most acidic proton is the blue proton. Okay? So I have given you in this video two examples that are important for you to take into account. Take-home message are, first of all, if you have more than one reactive site, Draw the potentials, conjugate bases, or conjugate acids, compare the stability. Now you know how. You know the factors. That's all you need to do. So, first, focus. Is the molecule acting as a base or an acid? If it's acting as a base, as in the case of the acetamide, draw the conjugate acids and compare them. If it's acting as an acid, draw the conjugate bases and compare them. Okay? So I hope this is helpful. Finally, I wanted to show you something that I also would like you guys to think about. Another set of reactions that we will see in the semester are reactions like the one showing in the slide. So let's look at the reactants over here. And this is how you will see how important is this chapter in the future. So when you look at these two molecules presented in this equation, I have hydrobromic acid. And the moment I see hydrobromic acid, you must understand that this is going to be acting as a Lewis acid. There is a difference in electronegativity over here. This is the acidic proton. If hydrobromic acid is acting as a Lewis acid, then the alkene must be acting as a Lewis base. And once you look at the alkene, you need to think, if it's acting as a Lewis base, it's donating electrons for a new covalent bond. In this molecule, electrons will be donated. Obviously, the pi electrons, because those are the ones farther from the nuclei, the ones that are easier to be donated, less tightly held. See how you reason these reactions. Now, if the pi electrons are going to be acting as a base, these two electrons are going to be given to form a new covalent bond with a hydrogen. That's what I'm indicating in this curved arrow. This bond is going to be broken. That's going to be forming a new carbon-hydrogen bond, and then one carbon is going to be left with a positive charge. This is a carbocation. So if you react an alkene with a hydrobromic acid, you will be forming a carbocation. Obviously, you can quickly think carbocation is highly unstable, 6 electrons the valence shell. So this will have to react with something. Well, once again, right here, you have another Lewis base acid reaction. Carbocation is a very strong Lewis acid, empty p orbital over here. Bromide, strong base, negatively charged. So what the logic here tells me that one of these electrons will be bound over this carbon. The carbon will be having a full oxygen. You will have a new covalent bond between carbon and bromine. Frankly, those are the reactions we will see in chapter 6. So that's how you use this knowledge of acid-base reactions to reason reactions and mechanisms in organic chemistry. A very large number of reactions that you will see in organic 1 and in organic 2 are Lewis acid-base reactions. That's why I'm taking time on explaining this. And this is the reason that I will follow throughout the semester. So look at the structure of the molecules, determine who is the Lewis acid, determine who is the Lewis base. Once you see the acid, identify the acidic proton. Once you look at the base, identify the electrons that will be donated for the new covalent bond. And then you just follow your reasoning to draw the product of the reaction. That's the fundamental idea of this class. Okay. With that, I'm going to finish this video. And once again, it's important for you to practice this, since this will allow you to understand the fundamental ideas behind pretty much every reaction mechanism that we will be learning in this class in the remaining of the semester. Thank you.